Jack, and
John and Nicole.
okay, so we'll have a small presentation for 3, so everyone will get to be actively involved.
Okay.
Our question today is about looking at big things that are big, and things that are even bigger. And so the first thing we want to do is, can you tell me a number?
7.
7. Okay, that's a great number. Now, where do you usually start? Like when you were little, where did you start with your numbers? What's the first one you learned? 1. Okay, so how would you get from 1 to 7?
1, 2, 3, 4.
Oh, okay, so 1, 2. Okay, so Jack is still 7. I forget your names again, I'm sorry.
Nicole and John.
Nicole and John. Okay, Nicole, can you give me a number bigger than 7?
10.
10. Okay, so how do we get to that bigger number, John?
Well, you keep going the same way.
Keep counting, okay. So we're going to call these numbers the counting numbers. You've been using them since you were 3, 2, maybe 4, maybe who knows, 5, 6. So you've been using counting numbers a lot in your life. Now, can you tell me a really big number?
50.
50? Okay, so we could continue on. I'm not going to write every number up to 50, but 50 is a pretty big number. How about, do you think you could get one bigger, Nicole?
1,600,000.
Okay, 1,600,000. So 1,600,000. That's a pretty big number. We have Jack, Nicole, John. And what is your name?
Ivar.
Ivar?
Sveto.
Stella.
Yes.
Okay, and Chris. Thanks for being here today. Glad to have you. We're looking at big numbers. We're going to be looking at the relationship between numbers. So we've been trying to see how we can do for getting big numbers. So, Ivar, Nicole just gave us a number 1,600,000. It's a pretty big number. Do you think you could get any bigger than that?
Yes, 1 Google.
1 Google? Well, tell me, what is 1 Google?
It's a 1 with 100 zeros.
Okay, so I'm a little lazy. I'm not going to draw 1 with 100 zeros after, but we know that it's 10 to the 100 power. So that's a very big number, right?
Yeah.
Okay, do you think that you could get any bigger than 1 Google? Why could you do that?
You can just keep going.
You can just keep, what do you mean like we can keep going?
You can just keep counting. You
Just keep
going
counting.
over and over and over.
So you think you could have this number, what's the number you could add to it to make it bigger?
5.
5, okay, so 1 Google plus 5, that's bigger, right? How about, do you think you could get any bigger than 1 Google plus 5?
Yes. 10 Google.
Oh, 10 Google, so you were going to have 10 times 10 to the 100, that's true. Now, Jack, can you get any bigger than that? What can you do?
10 times 10 times 10 times.
Oh, okay, so you're going to keep doing that. I kind of really liked what you did earlier. What did you just do to it? You just did something really simple. Just add a 5. But we have to so here we have 10 Google plus 5. Did he beat you? Did he
I still have more up my sleeve.
You have more up your sleeve? Okay, so what do you think, what are you going to do? What's up your sleeve?
20 Google and 20 quadrillion.
Well, this is a very, very, very large number. So we have 20 times 10 to the 100 plus 20 quadrillion. Do you know how many zeros are in a quadrillion?
No.
Well, it's right to you.
But I know how to spell quadrillion.
Well, that is an excellent skill to have it. So, does it really matter how many zeros are in a quadrillion at this point? Do you think that Jack could beat you even with this one? With his strategy? Okay, so do you think we're ever going to get to the biggest number? Are we ever going to get to the biggest number? No. Never to the biggest number? You're sure? So we can keep going on and on and on forever. We keep counting and counting and counting and not get to the biggest number. Is there a biggest number?
Is that infinity?
Oh, so positive infinity. But now, does infinity work very well as a number? It's a good idea.
It always wins.
Could you repeat that, please?
It always wins.
It does always win, but does it work very well? If we had, is Jack's method of infinity plus 1 going to work?
No.
Is that always going to be Okay, so like, are we pretty convinced that we're going to have a hard time? Like, are we ever going to get? Is Jack's method always going to get us of adding 5? Whatever number Ivar says, Jack can always beat it by adding 5, or multiplying by 10, or multiplying by 20. Anyone have any other solutions?
Oh.
Ivar, you have an idea.
90 Googles, 99 quadrillions.
What is quadrillion? Is it the exponent of 40? Quadrant.
I don't remember how much zeros.
So we decided it didn't really matter that much. It's pretty big, right?
Yeah.
Okay, 99 quadrillion. But Jack, what are you going to do to trump Ivar?
Plus 5.
Plus 5. Okay, so like no matter what happens, we're always going to run out of. Like, we can always make a number bigger just by adding 5. So we're going to call these the counting numbers. Now, there's some questions that we have about the counting numbers. Because there's some things that we can do. So we decided we can't ever get to the biggest. We're not at the biggest number yet. But I have a pattern that I want you to look at. So what if, from the counting numbers, I start taking just certain counting numbers? What if I just wanted to take like 2, and then 4, and then 6, 8, and 10? What could I do? Like, what do you think? Like, what's the pattern? What am I doing?
Those are the even numbers.
So those are the even numbers. What do you think the biggest even number? Like, do you think there's the same number of even numbers as there are counting numbers?
No.
No? Tell me, what do you think? Why not?
It's better if I show it.
Or you like to show me? Okay.
Because look, this is the first one.
Mm-hmm.
The second one.
Okay.
Why are you using your left hand?
It's a beautiful it's right here.
2.
Never using that hand.
Probably you can give her a balloon.
So what is your idea?
4. 5.
Okay, so
Because in these, this is like the largest number we have so far, but there's more even numbers.
so there are more even numbers. So I can keep this pattern going.
Yeah,
You want to?
like 12,
Oh.
14, yeah, 16, 18, 20.
So you're thinking that there are more of the counting numbers than there are of the even numbers?
Yeah.
And you're saying, is that kind of skipping all of these?
Yeah.
Okay. What do you think, Jack?
I think that there's the same number of each because it just keeps going on and on.
There's the same number, so it just keeps going on. Well, let's look at that question. We have a little conflict here. We have Ivar and Jack poised against each other, each with an idea. So Ivar is saying we're skipping every other counting number, right? And Jack is saying that it's going to keep going on and on, so that there are the same number of counting numbers as there are even numbers. What are you going to say, Ivar?
Well, you see, because 1 is the first number and it's an odd number. Because look, there's 5 even numbers and there's 1, 2, 3, 4. Oh, yeah, they're even.
I don't quite understand where you were going here.
They're even.
Between 1 and 10 is counting how many even and odd numbers.
Oh, so you're saying there are an even number of even and odd numbers. That's true. That's true. But if we keep going on, there's going to be an even number, or the same number of even and odd numbers in our counting set. Okay, so let's look at this a little bit more. We took even numbers, 2, 4, 6, 8, 10. What would the next one be?
12, 14, 16.
Okay, so there's a group of even numbers. And let's start counting the even numbers. So the number 1 that's going to be paired up with
2.
2. The number 2, you did a kind of a nice job here of counting even numbers already. I'm going to take you a different direction a little bit. The number 2 goes with
4.
4.
The number 3 goes with 6. 6 goes with 12. The number 7 goes with 14. The number 8 goes with 16. Then 18 and 20.
So is it going to go on and on?
Yeah.
So what do you think? What did Jack say earlier?
There was the same number, but first of all, there was like, let's see, there was like one Google.
So let's not go to one Google. Let's look at numbers that we can think about.
Okay.
Okay, pretty easily.
Let's say there's 100 numbers.
What if I told you I had a number down here, n, or so if I have a number n, what unit number would it go with?
2?
Goes back here to 2?
No.
What are you thinking? John, Jack.
Well, you'll never know unless you put a finite number out there.
Well,
Because as long as you keep getting
It's
bigger,
bigger,
you'll never know. Which, if there's more even than counting numbers.
well, so n is our counting number. We're looking at so in this pattern down here. So we saw 1 with 2.
So it's 2n.
Oh, so it's going to go with 2n. So, could I add one more? N plus 1. Then it's going to go with 2n plus 2. So, it looks like for 2n, or if we look at the even numbers, the number of even numbers is equal to the number of counting numbers. Does that surprise you a little bit, Eva?
Yeah.
That wasn't the conjecture you made at the beginning. Is it a little surprising?
Yeah.
Okay. Should we try, what's your favorite number, Jack?
3.
3. That's a very nice favorite number. In the last session, the person's favorite number was 19. And we had a delightful time choosing multiples of 19. So, in our new set of numbers, we're going to start with 3. Then we'll go to
6,
6,
9,
9,
12,
15,
18, 21.
Okay. So, we have a set of numbers. 3, 6, 9, 12, 15, 18, 21. This we're choosing every third number. Do you think it's going to have the same pattern? Do you think that there's the same number of multiples of 3 as there are counting numbers?
Yeah. Oh, no, because think of 100 numbers. Half of them are odd and the other half are even. But if you add them up, there's 100 numbers.
Okay. So for 100 numbers, does it work? It doesn't work that way, does it? But what about if we're thinking about all the counting numbers that we could possibly have?
Let's see.
What do you think? Do you think it changed in the situation, Jack?
Yes.
Tell me what changed.
I think there's less multiples of 3 than odd numbers.
There's less
Because
multiples of 3.
it takes less time to get to 100.
Oh, okay.
So what if it's not 100?
So
There's no-
it is true, like when we get to the hundreds, if we are only counting 100 numbers, there are fewer multiples of 3, and there are fewer multiples of 200. But what about if we're thinking about, what's the biggest counting number we could get to?
10.
Well, like at the beginning, we had 10 Google. We had 10 Google plus 20 quadrillion, and then Jack back here helped us out by adding 5 to it. Then we proposed 20 Google plus 40 quadrillion, and then Jack helped us out by suggesting we could add 5.
So additional multiplication doesn't help us.
So let's let's start counting these numbers. 1 is going to go with
3,
3. 2 is going to go with
6. 3 is going to go with 9. 4 is going to go with 12. 5 is going to go with 15. 6 is going to go with 18. 7 is going to go with 21. 8 is going to go with 29.
okay. So then if we have n, what would n go with?
21.
Or 20.
3.
24. It's arithmetic progression.
What would n go with?
I don't know.
So when we have all the evens, and up with
3n.
3n. Okay. of 3 as there are counting numbers? Because we can keep on adding counting numbers and keep on adding multiples of 3. Okay, so Bob and Alan, do you have any thoughts?
I'm not totally convinced yet.
Oh,
We're leaving out two numbers in between each of the multiples of 3. Do we really have as many counting numbers as there are multiples of 3?
we do. Yeah. Are you convinced? Are you convinced? Because you were skeptical. We were only looking at 100.
I'm not convinced because half of the 3s are from 1 through 10. There's only half of the 3s there.
It's only half. Through 1 through 10, there's only half of the 3s there.
Yeah.
But you should get a way of thinking of 3 and 2 because those are essentially the same numbers as n and n plus 1. All they give is just 2 and 3 in front of them. It's like an arithmetic progression. It's like a formula. Look, 2n, if you hide 2, it's exactly n, isn't it? If you hide 3, it's exactly 3. Here you can take out 2 in front of it, and it will be 2 plus n plus 1. The same thing. We can go on and on with every number. That's why we get the same number, I guess. What do you mean?
I'm convinced.
It's always good to listen to your father. It's important.
Keep going.
Okay, well, let's so what about if what are some other numbers? Like what's on the other side of all of these numbers? That's a good question. What is the opposite of this number? Out.
-1.
-1. So we have all these counting numbers here. We have all these opposites of the counting numbers too. So if you go to like -1, -2, -3, -4, do you think that we're going to have, does that change the number of numbers that we have? You go.
Yes,
Yes. Tell me why.
because you see 1 through 10 goes from left to right, and it's going up, like think of reading the book.
Okay.
You read left to right.
You read, I agree. But what about if you were in Japan?
Oh, other way around.
Oh, well,
So they will be like from left to right on the negative side.
oh, okay.
From right to left.
So how do you think that's going to change the number of numbers we have?
There's going to be less numbers.
There'll be less numbers.
Like it would be better to explain it if you put a 0 in between -1 and 1.
You really want a 0 here?
Yeah,
Okay.
that'll explain it better because you see, there's nothing after. There's no. If you add 0 plus 0, it's 0, and if you add -1 plus -1, it's -2. And I think negative means like let's think like if you have 3 barrels of water.
You
forgot the question. I think you're going on a tangent.
It does seem a little tangent-y, but sometimes we like to see where these tangents go.
And then if you drink them all up, it becomes minus.
Oh, so you were saying, are you sure it becomes -3 barrels? I thought it became 0. You drank all the water. Where did it go?
Well, then
But so here's my question for you. Oh,
and then you like get thirstier and you lose water from your body.
oh, okay, so it starts to disappear. So here's my question for you though. Remember how we were counting? We were doing a lot of counting. We were trying to figure out we started off by saying, what's the biggest number we can count to? And you gave some very big numbers to count to, but Alex back there could keep getting bigger, could keep getting bigger. He was really good at thwarting your efforts. He was very good at thwarting your efforts. But now, like, we've just added a different set of numbers over here. We've added some negative numbers. Did we change the number of numbers that we could count?
Didn't we double it?
Did we double the number of numbers that we could count? That's a very good question.
I don't think
What do you
so.
think? You don't think so? Why not?
Yeah, because if you add negative, if you can't add -2 with 3. It's just impossible. But you can minus them. -2 minus 3 equals 1.
You don't have to add them. You don't add them, just count them.
So we're looking to count our numbers, you know.
But we're counting, you know.
It's like you have a lot of Legos, and you decide you're going to count all your Legos. And now we've added this wacky notion you can have negative Legos. Do you have Legos at home?
Yes.
Do you have any negative Legos at home?
Maybe different color. Maybe different color, maybe.
A different color of Legos. But so we're kind of adding this, and you can count your Legos, and you can stop with your Legos, right?
Yeah.
But with numbers, when we had all these counting numbers, did we ever get to the end over here?
No.
But now we've added a whole other set of numbers over here.
So we cancel each other off, so we have no numbers now?
Well, we do have numbers. We still have, we want to count them. We want to see what happens. How can we count them? Do you think we're ever going to get done counting those numbers?
No, never.
Never done counting these
Yeah,
numbers?
because once I've heard a rumor that numbers never end.
You've heard that rumor.
Yeah.
Have you substantiated that rumor at all? Did you go to the source? Or was it a mean girl saying, numbers never end?
No, one time, when I was in math, I think I asked the teacher if numbers, no, it wasn't me, it was another kid, if numbers ever end. And I think she said no to most people, but to some people, if they count every day, like, to a certain number, they might get to the end.
Okay, so if they count every day to a certain number, they might get to the end. But most people might say no. Did you tell that girl that she shouldn't be spreading rumors in school? Did their teacher say, come on, stop that rumor spreading?
No, it was actually the teacher who said.
The teacher was spreading rumors, oh my. Did you say, shh?
No, she actually said it was real.
Oh, real. Oh, so she substantiated the rumor. Like she said it was real. Okay, that's good. Okay, so we're on this rumor that we can't ever stop counting. So we started with the counting numbers 1, 2, 3, 4, 5, 6, 7, 8. And we were pretty good at counting those. We decided we'd never get done counting. We've now added all the opposites of those numbers, and we want to figure out how many of those there are.
Do
So
you
we
want
want
to count it all together or just the left ones?
we actually like to figure out all together, the whole side, both sides. And we have someone who says that we think that we doubled it. Alex, you thought we turned it to 0? No, who said we? That was a rumor I heard. I feel like I heard. What did you say, Alex?
What do you think?
If you get 0, if they kill each other.
Oh, that they cancel each other out.
Oh, so we canceled each other out, so we had no numbers. That was the
They're all
came from. But we want to see if we can count these numbers. Can anyone?
So this is your ultimate goal?
My ultimate goal is to count these and see if we have more of these numbers than we have counting numbers.
Chris, do you mean that you've got the 1, 2, 3, 4, 5, etc., all those in a box, and the -1, -3 in another box, and you're wondering how many are in both boxes all together?
Yes.
Okay.
We're trying to see what we can do. So, like, how can we go about counting those? Like, what number should we, for the negative numbers, what number should we start counting with? Okay. Alex.
Yeah.
Oh, I'm sorry.
That's good.
Jack, I'm sorry.
If you were counting with the negatives, you can't really start anywhere you're counting backwards.
So say more about that.
Because then you're like, it's the same as the counting numbers, just flipped over.
So when you're saying counting backwards, you mean start, what do you mean by counting
Like
backwards?
start with -1.
Because I don't want that point where you can't start anywhere. Like, because if we were way over here, what would be this number that we could be starting with over here?
You can't because it would go on and on and on.
And so because it's kind of the same, remember on that direction, you just kept adding 5. And then over here, we could just keep sort of adding a -5 and subtracting 5 and getting a different number. Eva, you played your hand raised very patiently. What were you going to say?
You start from 0 and
I don't have 0 here yet. I don't even want it. I don't know if
you start with nothing. Then it's better to show you.
Okay, so I want you to hold this thought. You really want to add 0, and I'm going to add 0 in a little bit. Let's keep that idea. But right now, I just want to see if I can count just the negative numbers, okay?
Okay.
So we'll put 0 over here as one that we want to deal with a little later. I want to go with Jack's idea. Jack said that if we started counting here, so the 1 goes with here. What number, where are we going to, which number should we count as number 2? Okay? So the -2 comes over here, or 2 to -2. Which number should be negative, or should be 3?
-3.
Okay? So, if we're counting that way, how are we ever going to start counting these numbers? What can we do? Because we're gonna, we can count all these numbers, and we have enough, do we have enough counting numbers to count all the negative numbers?
Yeah.
Yeah? Because we're never gonna run out of counting numbers. We're gonna have to count all the negative numbers that we've never run out of. There's this, but how are we gonna get a pattern that's gonna get us to count these?
N plus 1.
Say more about that.
Well, n is like the base, and 1 is with what each number is different from the one which is before. Like 2 is different from 3 with 1, and if n is the base, 1 is the difference to the next one. And I'm still stuck with the arithmetic progression formula.
Okay, so, and I don't know that was the best path for me to have gone down. It didn't appear to convince Bob. Well, so I guess really our problem with 1 is we can count all our negative numbers, but following this pattern, we don't get any of these that we've counted.
And you want to count those?
I want to count both sides, because remember these 2 boxes we're trying to count at the same time. All these positive numbers, all these negative numbers.
So it's always just double. I mean, there's always a positive to a negative, so.
It's true.
It's 2.
But our question is, if we have those boxes together, are they the same number? Like, how does the number of numbers differ from here?
It's 2 times this.
I think it's 2 times that.
Yeah.
Okay. So remember when I was counting all the even numbers? Did we say that we only had half this number of counting numbers?
No.
So even though we were skipping every other number, what number did we get this to? It was the same number as the counting numbers. So if we have 2 boxes, if we have both.
I think it's just agreeing with what you're saying. I think I'm hearing, not getting mishearing. I thought I was hearing that there are only half as many, that there are 2 and the counting numbers compared to the evens.
No, that is not true.
I thought that's what I heard, sorry.
Yeah,
Okay, maybe then we need to clarify that notion. Okay, so it's true. Okay, this is where I am. So here's n. We'll go back to where we were and I'll clarify this. So we had 2n. Anyways, we were counting. This became 1, this became 2, 2, 3, 4, 5, 6, 7, 8, 9, 10. The nth number they corresponded. There was a 1-to-1 correspondence here between n and 2n. And so, were there the same number of counting numbers as there were multiples of 2?
As far as we can see.
As far as we can see. So they're the same, the counting numbers and multiples of 2 are the same. We then took Jack's favorite number of 3, with the same number of counting numbers as there were multiples of 3. So now what we've done is we've added this extra set of numbers that at first glance maybe appears like we've doubled all our numbers. But could we still count them? Are we ever going to run out of counting numbers to count these numbers? No. But we just need to figure out a way to count them so we can kind of convince ourselves that we're never going to run out of counting numbers. This method of starting at -1 works pretty well. But as we keep going this way, we keep eventually getting this way. We've missed all the positives. Is there another way we could go about counting them, assigning our counting numbers to these positive and negative numbers so we could get both the positives and the negatives at the same time?
So do you want to put minus n at the end?
Well, but minus n isn't the most negative number. Because remember Jack always said we could add 5 minutes to it. Your insight at the beginning was very good. Because what did you say? We couldn't start way out here. What would happen if we started way out here?
And we always be missing a few numbers.
We'd always be missing a few numbers because we can't ever get to the most negative of the negative numbers. So you had to study in the middle. How can we count at the same time so we can get both the most negative of the negative numbers and way down here, the most positive of the positive numbers in our counting method? Evar.
0.
You want 0. That's what you want 0.
It's true. That's the beginning.
Nothing.
So how does adding a 0 help us count both the positives and the negatives at the same time?
It doesn't help us.
Okay. It's a great number to have. Very convenient. We'll use it momentarily. I have it here waiting to be counted. But let's see if we can figure out this counting problem right now.
It's different from the positive numbers because positive means like existing, and negative means like minus existing. If you think if you give points and you have 10 points and you minus 11 points, it becomes -1.
So you have a good understanding of how to do operations with positive and negative numbers. That's very useful. And so I'm going to want you to just think a little bit that I'm asking you a different question than that. Okay? So the question I'm asking is, how many numbers, if we've added all these positives and all these negatives, we want to count them up. And we want to see if the number of positive and negative numbers is bigger than just our counting numbers. Jack, that's us off to a good start. We start at -1, we can get all the negatives. What could we do next to help us get, in our counting, to help us get the positives? We start with -1 on the negative side. What might be a logical one to go to count as number 2? Jack?
Just go -1, 0, 1, 2.
Oh, okay, so let's skip 0. We don't have it yet. But then, so you're going up in the line. So you're going to say 0 should be 2. 1 should be 3, 2 should be 4.
So should we start subtracting the numbers going to the negative? Like when we, from -1, if you subtract -1, we get 0. From -1, if you subtract -2, we get 1. Then we'll start going counting to the right.
So you're saying that if we had a machine that was counting for us, if we put it in the -1, that would be assigned the number 1. And sorry, I didn't fully.
So we have -1, -2 will count to the right. And at the same time, -1, -1 again. So we get 0. Can we count like this? We count in this direction. Or can we start counting parallel? So the next step will be -1, -1, so this is 0, -1, -2, this is 1, -1, -3, we'll count 2. This is not the solution. You said that's how.
Okay, this is pairing them up.
Is our goal to count both sets at the
Yes.
same time?
Yes.
So how many processes we can start? What are the rules? Should we go in one direction, or we can go?
Or could we go what? If we go in one direction, is that working for us?
No.
So what could we do instead of going in one direction?
I'll suggest to start 2 processes. One is going
That way.
that way, and the other one will go that way. But when we extract that.
Okay, so this idea of 2 processes is one that's going to be useful. Like this idea of 2 processes, kind of going at the same time. If we go this way, if we start at -1 and go this way, we know that we're going to get all the negative numbers. If we start at 1 and go this way, are we going to get all the positive numbers? Yeah, okay, so we've left out 0 first. So if our first number we count, let's keep with Jack's idea of having it still be -1. How could we run the second process at the same time? So if 1 goes to -1, what will 2 go to? 2 can go to 1. What would 3 go to?
-2.
3 could go to -2.
And then 4 goes to 2.
4 could go to 2. 5 could go to -3. 6 could go to 3. So I'd use the word math because it's a bad word.
Oh, hand,
What would you say?
hand.
Hand-holding. So, hand-holding, I've watched this morning, and I'm now attempting to replicate the lecture and build on it. So, I have the experts right here. This is my first time.
You guys are.
You're the experts. I'm helping you to think about this. So, if we pair them off, so the 1 ends up holding hands with 2, the 2 ends up holding hands with 1. Each one is going to be, are we going to run out of counting numbers? And so, what's the size, how many, is the number of positive and negative numbers different than the number of counting numbers? I see John saying no. Why do you think no?
Because there's always been the same number.
Can you say one more time?
Just because as long as you can keep getting bigger and bigger, you're always going to have the same number. You'll never be able to prove otherwise.
Okay. What do we think?
Isn't that like the example with the odd and with the even numbers? We showed that even numbers are the same. They have the same count as all of the counting numbers.
So the even numbers are the same count as all the counting numbers. And the positive numbers and the negative numbers, are they going to follow that same pattern? Or are you suggesting that they follow the same pattern?
They did.
Yeah, they
1
did.
goes to -1, 2 goes to -2, 5 goes to -3.
So they all correspond, they all can shake hands with each other. So we have a lot of numbers, but are the counting numbers the same as the positive and negatives? Yes.
Yes.
I see a few heads nodding. Okay, now how about if we add bar 0 to it all? What can we do with that?
Chris, before you get to that, just to make sure I understand what's happening. If there's a knock at the door, and it's FedEx, and FedEx comes in with a big box of the counting numbers painted red,
Okay.
all just amount of table. Here are
It's a really big box.
the really big box. Here are the red county numbers you ordered, Chris. Thank you. Chris, knock at the door. It's UPS. The big box of green county numbers. Here are the county numbers you ordered, Chris. 2 boxes on the table. Red county numbers, green county numbers. And you say, gee, thanks a lot. Oh, this is really insane. They go, like, you wonder to yourself, how many do I have in these 2 boxes? What's the answer?
I have the same number as I have in, do I have the same number that I have in one box?
You have the same number in both boxes, but if you had, yeah, pretty much, yeah. If you,
If you don't know the answer, it's you
um,
can listen.
like the green are the negative and the red are the positive,
Okay.
and each of them has the same number.
But altogether, how many do you have?
0 actually, because if you add them up,
No, you don't have to.
Just take the 2
Oh,
boxes,
oh,
pour them on the floor.
twice is all the numbers are on the world.
So I was afraid of. I wish I could just count the red and the green numbers. They're all, I hit the table by mistake, they all spilled on the floor. It's like
I mixed them all up. And they turned brown.
No.
Pixels turned brown. Now you have to count them all.
Can you count them? How many do you have? Do you have twice as many as you wanted? You just want the county numbers. Do you have twice as many as you wanted, or what? Yeah, you're right. The red ones are the negatives and the green are the positives. That's what I have in mind. But I'm just not totally clear in my mind how many I got all together. I wish I had a way of counting them, picking them up.
What can we do?
Look on internet.
Well, we can answer many questions. But let's see, what can we do with your thinking?
You need a supercomputer.
We keep working, but then we always have problem +5. So we have them all mixed together. I haven't convinced you.
Need a method for picking them up. Pick up sticks.
Well, so what should I start doing? So I'm just going to count them all there.
Yeah, you're going to count them all, but you're going to sort them on different things. Then you like add them up and you have twice as many as you wanted. But if you add them all up, then like 1 and 1 will be 2, and 2 and 2.
So these are pieces of wood. These are made out of wood. I can't add them. There's chunks of wood. Red chunks and green chunks. And it's a mess on the floor.
You can glue them.
Could you?
And then you've got a whole pile of wooden numbers on the floor, and you wonder how many there are.
Yeah.
And so, if it were me, but that's because I'm a housewife, I'd pick up one, and then I'd pick up another one.
With both of your hands.
No, I guess when you're counting, you do one at a time. The first and the second.
So you want to count them in pairs?
No, I'm just gonna count, I'm gonna pick up a green one, and then maybe another green one, and then a brown one, and
So I have my mix-up box.
So you're picking up a red and then a green, a red and then a green.
Well, maybe not. I don't have to pick up any of these particular order. Like,
So I want to keep track to figure out how many I've got.
so
I had twice as many as I wanted, or I had half as many as I wanted, or I had exactly as many as I wanted. I don't know.
So as I keep picking them off, I put them in this box here. I'm using, which numbers am I going to use to count them? Am I going to use the negative numbers to count with them? Did you, when you were little, did you count with negative numbers? Did you go
No.
-1, like go -2,
No.
-3 pennies, -4?
No,
No, not very often. How about you in the back? Do we count negatives there?
I've got a theory now.
Well, mini theory. Well, so let me just keep with this idea, and then we'll get to theory in a moment. So we're not going to count using the negative numbers. We're going to count using the counting numbers. So if I keep counting with these, so I've gotten all my red ones, all my green ones. I start counting them with the counting numbers. We're going to start with 1. We're going to go to 2, 3, 4. What's going to come next, Eva?
5,
5. Jacqueline, who's next?
6,
6. Nicole, what's going to come next? 7. John?
8.
8. I'm sorry, I can't pronounce your name.
So,
7. What'll come next?
after 8, 9.
9. Okay, so we've got, if you're all on board with this counting regime, what number am I going to get to once I've counted all these numbers? Will I get to the end of it? So is it going to be the same number
Lots
of
of flows.
numbers in here as I would have in my counting numbers?
No.
So I keep counting. Do I ever going to run out of counting numbers? No. So I just keep counting these. Like I'm never going to run out. I'm going to get to the point where they're the same. Eventually. Maybe. What do you think? The beauty of painting oneself into a teaching box.
I guess I would want to be systematic and pick the things up off the floor in some sort of way.
You want to pick them up in some sort of way? Well, what about if we reordered them? We had a lot of time when we put them back in order. Went back to the system. So we know that the 1 can go with -1, the 2 with 1, the 3 with -2, the 4 with 2,
Sounds good.
5, -3, the 6 with 3, 7, going to go back over to -4. This way I make sure that I don't miss any, none will let it go to bed. It would be if you don't get stuck, they didn't get stuck in your foot while you were like, trying to organize them. Your little boy didn't come and chew one, eat it up. But, so we have this, I'm not certain I convinced you.
So we have the same count of numbers.
The same kind of numbers. Like, even when we've added all these extra negatives here, we have the same count of numbers as the correspondence. They go, all counting numbers can be assigned to one of those numbers. Since we never run out of counting numbers, it's going to be the same number that we have here.
Because we're skipping 1.
Not because we're skipping 1, but because we're never going to run out of these. We can just keep counting. We can just keep. You can always add 5 more of these. You can always add 1 more counting number. And so it's always going to allow this number to be the same. We'll never end.
So what's the answer, 10?
No, I should not have done that. Upon reflection, a bad way of watching this. I'm not convinced you. And now when we go, if we try to go 2-dimensional, heaven forbid, what am I going to do?
Well, actually, let me pick up your idea of gluing, which is a nice point. You said maybe you could glue these together. What if you had the counting numbers coming through this door, and the negative numbers, see the door that's not there?
Imagine the door.
Yeah, the negative numbers coming through the door that's not there, and the -1 comes in, and 1 comes in. Gotta have one of them come in first. Let's say, even through this door, always come in first. 1 comes in, holds hands with number 1. Negative number comes in, holds hands with number 2.
Girl and the boy, you got married. They go out from this.
But it might be that you're able to pair these 2 columns of numbers coming in with, and say, first, second, third, fourth, fifth, sixth, seventh, eighth, and that way, oh, we've counted them all. Every student, we've got all of the positive ones, we've got all the negative ones, we've been able to say which is the 19th, which is the 201st. So we counted them all.
So it's like a ribbon with two branches.
Yeah, exactly. Time was in the 40s.
So we have the great Mississippi fall down.
Yes.
You feel? Like we have, are you convinced? You're willing? You're a very agreeable group.
Throwing zero, that's everything up.
Throw in zero. What should we do? What happens if we add zero to this mix? We've had all these nicely paired ones all along. But now, here comes zero.
Zero is long.
Add one at the very end, when you finish. And that's zero.
Okay, add one. Are we going to get so like that strategy is called? What if we never going to get to the end, so it's hard to add one at the end, but what could we do at the beginning?
Start with one. Zero is one.
Let's start with zero as one.
Two.
So just renumber our group, have zero coming along, it's like a minister, we could say that in the wedding party, the minister comes in at zero, and then starts pairing off all the couples to be headed on their way. So if we add zero to this group, are we going to have any more numbers than we did in this set of numbers? No, it's still going to be there. Okay. Now, here's the next question. What about if we have what about if we just look at a sort of small range of numbers? If we have, what are the numbers between 0 and 1?
What kind of numbers?
Well, let's say I'm sharing my lunch with you, my sandwich today. We had one sandwich, but I just had to share it with you. How much of the sandwich, what number we use to describe how much sandwich you ate? Half, okay. Well, how about, so 3/4? We got 3/4, you get 3/4 of the sandwich. What about, it's going to come in here. Well, okay, so then the poor soul over here, sharing a little bit. Now, what about this person really is not interested in their sandwich, and so they keep trying to cut off bits and bits of their sandwich? What would they get to? So if we have like half, what's half of before? 1/8. Well, so these numbers are going to get pretty small, pretty fast. So like, we have 1/8, we could cut that in half, we could.
So you can never get to 0.
1/16. So we're not going to get to 0 so much, but like, are you sure? Like, Yvonne, what's going to come next if we keep cutting it in half?
I just want to tell you something else. Picture a loaf of bread.
I see a loaf of bread, thank you for.
And
Is it a lot different than a sandwich?
Yes.
A much better loaf of bread than my sandwich.
Yeah.
Okay.
And you're cutting off little magnifying pieces of crumbs.
Well, so what fraction of a loaf of bread am I, or are those crumbs?
Well, 1 out of infinity, if it could out of 1.
Did we talked to, does infinity work very well as a number
No.
for us? We have a hard time counting infinity. So what fraction should?
1 Lugo, 1 out of 1 Lugo.
Oh, it's true, but so it's pretty small. Those are some pretty small numbers. What if we do, what if we keep following this pattern now? It's gonna, if I cut this in half.
Oh, 8.
Well, I already have 1/8. What would be small? If I cut 1/16 in half, what would I get to?
8.
That's interesting. You have an interesting notion here. If we have, so here's my square sandwich. Does your mom ever cut sandwiches for, like, my little boy, 4 years old, he loves to have his sandwiches cut in X's and T's, actually. So, did you ever ask for special sandwich cutting when you were little?
Never.
You never asked for special sandwich cutting. Well, in my household, all the toast and all the sandwiches always have to be cut. And you would get an X, and then we get a T. And so how many pieces of sandwich does my little boy always have?
8.
8. So one of these pieces would be 1/8. Now let's say that my little boy was, like, his name is August, and he said, Dad, I really want even smaller pieces of sandwich. What could I do?
It's better if I, like, go up.
What could I do to each piece of sandwich you buy? Now, do I know how big this piece is?
It's 1, 2, 3, 6.
Also, each one of those is 6?
Yeah, and 6 times 4 is 24.
Oh, so I can get to 124. You used it. Like, it works. Like, it is true. If I did this pattern, we end up at 124. So 124 is smaller. What if you cut each sandwich oddly into 1.5 pieces of the same size? Finish shaper. If I added, what if I cut all your sandwiches in half again?
Then you will get 12 times 4, which is 48. So you'll get 48 pieces of sandwiches.
Okay, 48 pieces of sandwiches. And he's just going to get 1. Are our sandwich pieces getting pretty small?
Yeah.
Or is this going to be a filling lunch for you? No, it maybe fill, like, it might feed your mouse. Maybe a grasshopper. It might feed an army ants in my school. Definitely 1/48 sandwich would attract several thousand ants to it in just a moment. Maybe it was the flaming hot Cheeto we had the screen outdoor. So we have a lot of fractions here. Do you think we found all, like, are we getting any closer to 0? We're getting closer to 0, but are there any fractions that could be in between here? Do you think we have found all the fractions? Have we found all the fractions?
No,
You don't think we found all the fractions?
no. I don't think we found all the fractions.
Okay, is our method working super well for coming up with all of them? Are we doing a very good system for making certain that we found all the fractions? Like, if we keep on going on this path, this is going to get us all the fractions. Keep on sort of occasionally multiplying by 1.5 and then dividing by multiplying by 2.
Thank you.
Oh,
He's tired, sorry.
sorry.
Thank you, please.
Um,
You guys.
So you never get to 0.
we don't get to 0. We haven't found all the fractions. We want to find all the fractions. Let's come up with a way to, our first step is to figure out if we can figure out a way to find all the fractions. It was pretty easy to find all the counting numbers because we just had to add a dot, dot, dot at the end, right? Then when we added all the negatives, we just added another dot, dot, dot down here. You can imagine we found them all. Now what we're going to do is we want to, so we have these fractions, we haven't quite found them all yet. Like what's going to be, like what's an easy fraction?
Half.
Half, okay. So half is pretty easy. So this fraction has what in the numerator? 1. And so could we come up with another fraction that has 1 in the denominator or numerator? What's kind of the next one then? Oh, 1/4. What's one that would maybe be in between here, but there's 1 in the denominator? Jack.
1/3.
1/3. What would come next?
1/5.
1/5. 1/6. 1/7. 1/8. 1/9. 1/10. 11. Okay, we're doing pretty good here. Are you ready to? Can you tell me the patterns here, Nicole?
1 over the number plus
Okay, 1 over the number plus 1. Can you say more about that? Or what would you think? So, like, can you tell me what's the next number going to be?
1. Yeah, 1 over 13.
1 over 13. So the bottom numbers are just following the which set of numbers, the counting numbers. Is there anyone that we might have missed over at this end? Oh, so we can't have negative ones, but let's see if we just deal with the positive ones. Right now, what we missed right here? 1 over 1. Okay. So now are we ready to resort to dot 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 in this row? Okay, so could we come up, are there any other, so we have a lot of fractions here. A whole lot.
Going up that way?
Well, so we could,
But that's the direct. No, but I mean, because 1 over 1, I thought wasn't that.
Because you're actually going to 0 to the right.
Yeah.
we are, it is true, they're getting progressively smaller.
Oh, okay.
We're trying to come up with ways to just, or make certain.
There's got to be a circle involved, not like number 0, but like, because math people always put a circle where there's lines. And that's how we turn it into a real math.
I'm sorry,
I was
there's
just thinking there's got to somehow be a circle
Oh,
involved in the theory.
we're going to go back, we're going to circle back, it's going to circle back on itself.
No, it's a pie.
Yeah.
Yeah, we were thinking, is it
Yeah. Yeah.
Yeah, you start, normally they do fractions when you're small with slices of a pie.
Oh, right.
Now they do slices of pizza because it's modern.
Oh, right. It's learning.
So, do we have all the, in this line here, do we have all the fractions that have a numerator of 1 or a top number of 1?
No. So we can keep going.
Well, we could keep going, but if we use our magic dot 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 to keep us going. But is that all the fractions that we can have? Because what else could we have?
That's all, because we put the dot, dot,
What about 1 over 2.5?
Oh, there's that whole question. What about if we had, do all fractions, like you, for instance, someone got 1/4 of the sandwich, but someone else got what fraction of the sandwich?
That 1/74 or something, like that.
1/74 by the yeah. But if someone got 1/4 and we had started the whole sandwich, how much did the other person get? 3/4. So is 3/4 of this list of fractions? No. So how could we
What
start?
is that 4 and a half?
So we have a 4, but we don't have the one that goes pairs up with it to make a whole 3/4. What about if you had let's see what we think. If we had or like the number of us in here, what about if we just had 2 people leave? How many of us were here to begin with? 7, 9. There were 9 of us here to begin with. 2 of us left. What fraction left? 2 ninths. Do we have that number in here? Like, what could we do to our list to help us generate all the fractions? So we could get 2 ninths in our list.
Well, if we paired all of them up, that would be
Parent, it is.
Or you can change your numerator to be your counting numbers too.
Oh, if we can change our numerator to be our counting number. So this top row, we're changing our denominators. Do you think we could add another dimension where we're changing our numerators? So if we were going down, the next one would be
2 ones,
2 ones,
3 ones.
3 ones, 4 ones, and conveniently, dot, dot, dot.
Counting numbers.
So now we're just going to continue this on. So we have 2 ones, this is going to be 2 twos, 2 thirds, 2 fourths, 2 fifths, 2 sixths, 2 sevenths, 2 eighths. Wait. I'm just going to keep that one going. 3 ones, 3 twos, 3 threes, 3 fourths, 3 fifths, 3 sixths, 3 sevenths, 3 eighths, 4 halves. So now, if we follow the system, do you think we could come up with every fraction that existed? Are there any possible ones that we're going to miss?
Would 7 or 19ths be on there anywhere?
Where do we think 7/19ths would be?
Well, right.
So where do we have to go?
If you're further to the right and down.
So we go, here's 12, 14, 15, 16, 17, 18, 19, then
Seven.
come down to row 7. Okay, is there any fraction you think that we're missing out here?
There's lots of them.
Well, tell me one, let's see if we can find it.
2 nights.
2 9s, okay. So 2 9s is not up here. Do you think there'd be, following the system, we would generate it eventually?
It's that first stop.
Yes.
So here,
Yeah.
would we come over to the 9s, go down 2 9s? Okay. So these are just the fractions, these are for all the fractions that we can think of. Now our question is, do we have more numbers here than we did with our counting numbers? Same. How could we start counting our fractions? How could we start pairing them up with our counting numbers to see, like in a way that we can make certain that we count them all? Has it worked for us when we started way out here? We started at the biggest fraction we get, but this actually would be a very, very small fraction. Can we start out here and count in?
Yeah, you have to start in the upper left corner. And
Upper
then
left corner.
take that one, and then take the one to the right, and then one down. No, one to the right, and then go back and go down one. Then you can go down again, and then up. So you're going, so you're basically going diagonal.
Oh.
Diagonal lines all the way down towards the lower right.
Okay.
So draw a line, diagonal line each time.
So so like this, then that.
No, just
Just like you were doing.
Oh, just like I was doing.
yeah, just draw, and then go to 1/4 and draw a diagonal all the way down through 4 ones. Yeah.
Okay. So is this method going to work to count? Bob's mom always told me when his rooms were he needed to clean, start in the corner of his room to start cleaning. Okay, let's see if we start here in the corner. So the 1 goes to here. We get 2, 3, 4. What do we do about 2 2s?
Count it.
Counting? Well, we've already counted 1 Could we go through it and just skip it?
Sure.
Do we have to assign a number?
Why do you want to skip it?
It's a number.
We've already had it.
Oh, it's in the school.
Okay.
Hey.
Also, no one has levels.
But then you also have to all figure out what you do kids all the time.
So that's a problem. Like, what can we do in this counting method so that we have a lot of duplicate fractions here, or values that are equivalent?
Just go at the top row.
So this method is going to get us through all the numbers. What do we do when we run into a duplicate? What can we,
I guess skip it like you said.
like, sort of, I told you the answer, this is the best teaching method.
They're easy to kill, like it goes 1 over 1, 2, 2, 3 over 2, 4 over 4, so you can do mass erasure.
Mass erasure, so we
Take the
can
whole diagonal one of these right.
take that whole diagonal out, take out this
Yeah.
kind of diagonal thing. You find that pretty easily. So what do we want to say about these numbers? Like, are there more of these numbers than our counting numbers? No? Yes?
No.
Why don't we follow your path and tell them?
Okay, so 1, 2, 3, 4,
Skip that.
6, 5,
Yeah.
6.
Skip.
We don't have 2/3.
Oh, 2/3, sorry, that was 3/3.
Yeah, that. 7, 3 halves, 8, 9. We come down here. Are we going to be able to find a number for each one?
For
we've done this. We've counted this. So our question is, we found, does every number, have we found any big number that's even bigger than just the counting numbers so far? So all the sets of numbers we've looked at so far, which are the counting numbers, I guess we'd call these the natural numbers, without the one, adding 0 in. You solve that problem very quickly and easily. The integers, all the negative numbers, we have the same number of numbers as the natural numbers. And now,
And the evens and
the evens, the odds, what are these numbers called?
Fractions.
Fractions. They have the fancy word as rational numbers. Like they are all a ratio of each other. So all of those numbers that we've seen so far have the same number of numbers as the counting numbers that you started with when you were 3.
what about negative rationals also?
Well, do we think that's going to be any different than the negative? Because I could just make this same chart, same array over on this side. Are there going to be any more negative rational numbers than there are counting numbers? No. So what do we think? So we found a number that's bigger than the numbers you started counting with.
Wait a minute, what about negatives and positive rationals?
Oh,
That would be twice as many.
you think this is really going to be twice as many?
Well, you got them all on the right-hand side of the board, you got them all on the left.
What happened when we had all these other our fabled boxes of our fabled FedEx delivery of numbers? Did it increase? Did it double our number of numbers when we tried counting them last time?
Got a lot.
Got a lot, but it didn't double them. It's just kept us the same number of numbers. The big thing is so now, like, our question is, where do they ever get bigger? Do we ever have more numbers